Hello everyone, my name is Wim Martens and I want to talk about representing paths in graph database pattern matching. So this is joint work with Matthias, Tina, Carlos, Stijn and Domagoj. So graphs are really everywhere, right? All kinds of networks can be seen as graphs. The web is a graph, program flow is a graph, and if you take transactions, financial transactions, then graphs are also very interesting to detect fraud detection. And graph databases are about querying these graphs, right? And one thing that graph databases are really good at is reasoning about connections in your data. So in a sense, they bring the capability of reasoning about these connections to the masses, essentially to anyone who can use a database. And this is why paths are very important in modern graph query languages, because paths are really the connections between points in your graph, right? And they are so central in the language that the language makes it really easy to query them. So they use these visual patterns to query paths. For example, this pattern here, it searches for paths that start from some account X, and these paths have length 0 to 5, and they end in another account Y. And there are paths that start from a blocked account. All right, and now there are two ways of querying paths, roughly, in graph databases, and the old school way has been about querying endpoints of paths. So there the philosophy was that you ask queries such as return all the nodes X, Y, such that there is a path of transfers from X to Y, right? So in this graph, you would get Mike, Scott, because there is a path like this here, And the new way of doing path queries in graphs is, well, paths have become more important. So you could do the same thing as before, return all the endpoints X, Y, such that there is a path and so on from X to Y. But now you can tell the query language or the query engine to also return the shortest such paths, for example. Right? So in addition to returning Mike and Scott here, we would get like the paths from Mike to Scott that have transfer edges. Okay, and returning paths like this is today possible in Cypher. It's possible in SQL with the new extension to PGQ in June this year, and it's planned in the upcoming GQual standard. And well, this all sounds nice, but how do you actually do it? Because one challenge is definitely that there can be a huge amount of paths between a given pair of nodes. So consider the following query here. This just asks for paths P from an A-labeled node to a B-labeled node, and then it wants to return all these paths P. But if your graph looks something like this, and it has like something like n nodes, then you're going to get 2 to the n many results of this form, right? Because in this graph, there are 2 to the n many paths from all the way to the left to all the way to the right. And as far as we know, current implementations even materialize all these paths, even for queries that don't explicitly need all these paths, like this one that just wants to count these paths. Okay, our proposal in this paper is a compact data structure for representing multisets of such paths, and we call this path multiset representations, or in short, PMRs. So how do we envision that PMRs are used? Well, normally when you answer a query on a graph database, then you have a query plan, right? So this is a query plan where on the leaves P1, P2, and P3, you have patterns that are matched against your data. And how does this very roughly work? Well, your patterns are going to give you a bunch of intermediate results. These intermediate results are passed on higher in your query plan, and you combine this with operators until in the end you get a result. Okay, this is more or less how it works, except that, well, as I just showed you, if you match a pattern, the number of paths that you're storing there, it can be huge, right? It can eclipse anything else. It can be exponentially larger than your data. And yeah, what we hope to be able to do with path multiset representations is essentially do the same, but then use compact representations all the way through the query plan, right? And the philosophy is that if you can go with drastically smaller intermediate results, this is going to give you a lot faster query evaluation. Yeah, and key properties of our approach are that our compact representation is lossless. Sometimes you need to do a little bit of computational work to get to the actual paths, but the goal is that we will be able to do query plan operations immediately on the compact representations and only unzip to actual paths when it's really needed. So what's a path multiset representation? Well, it has 4 components. First of all, a path multiset representation of a number of paths in a graph G. It consists of a graph R, which is the representation, and then a homomorphism that maps things in R to things in G. Yeah, and you have a set of start nodes and a set of target nodes. So let's look at a couple of examples. So in this example, we want to represent the set of paths from A to C in this graph here. Yeah, and this is one PMR that does it. So in this case, the PMR is actually a subgraph of G. Yeah, so the homomorphism is the identity. And then which paths does it represent? Well, in the PMR, you can take any path from some start node to some end node, and then you take its image under the homomorphism, which gives you a path in G. And these are the paths that are represented. Yeah. So this path here in your path multiset representation, it represents this path in your graph. Yeah. And actually all the paths in G are from A to C are represented here. Yeah, because here you have another path which corresponds to this path in G. And now you can walk this loop here as often as you want. Okay, let's look at a more interesting example. Let's consider the even length paths from A to C in this graph. Well, here is one path multiset representation that does this. So it's similar as before, but now the loop is longer. And now the homomorphism, it maps all the nodes A1 and A2 to A here, and B1 and B2 to B, and so on and so forth. Okay, and yeah, what do we have represented now? Yeah, well, this path in the multiset representation again represents this thing in G. The next longer path from A1 to C in the multiset representation is this one. And that path corresponds to this one in G. And this one has, for example, length 8. And yeah, this is an even length path from A to C. Notice that here, if we would follow the loop only once, yeah, then we would not get an even length path. So here the length of the cycle is important. You may think then, okay, until now we have been talking about just paths. How does the representation deal with multiplicities? Well, in my representation, I could, for example, just add one more path from A to C that is also mapped to this path ABC through the homomorphism. And this would mean that we are representing this path ABC twice. Okay. So in the paper, we provide a whole bunch of theoretical results that show that this approach is promising, right? And for example, we show that path multiset representations can represent any finite multiset of paths, also interesting infinite multisets of paths, namely the regular ones. They are never larger than the explicit list of paths that you're going to get as results of a query, but they can be exponentially smaller. And okay, if they represent something infinite, they can even be infinitely smaller, right? This here means that in terms of size complexity, that you have nothing to lose by using PMRs. You always get more, or you never get larger, yeah? Okay, and then in terms of complexity, well, if you start with a regular path query, which is like the basic building stone of graph pattern matching, you can compute a PMR for all the paths that it matches in linear time. Remember, current approaches for doing this actually take exponential time. Yeah. Grouping per start and end node is easy, and we have some other results as well. There is much, much more in the paper. Okay, so we also did experiments to see if the approach really works in practice. And so here is a simple query we ran on the Ego Facebook data set from Snap. Yeah, just returning up to 100,000 paths of length k from a randomly chosen node in the graph. And yeah, you see that using PMRs, at least we were something like 2 orders of magnitude faster than Neo4j. So at this point here in the graph, actually you reach the 100,000 paths. Okay, this second case here, we just wanted to count the number of paths of length k, and here the difference between just using path multiset representations and what you do in Neo4j, for example, was even bigger. Yeah, so here we got 4 relatively short paths already with differences of 3 orders of magnitude. And well, the difference will only increase if the data gets larger, because we have a linear time approach versus an exponential time approach that other systems have. Okay, so notice that this is a log scale. Okay, we ran another experiment on larger size data, because the Facebook data set is not so large. And this one was also with real world queries. So we took a bunch of regular path queries coming from timeout queries that we found in actual query logs. And we wanted to compare our performance to Neo, Jena, BlazeGraph, and Virtuoso. Now, notice that out of these candidates, only Neo actually supports a query language that can return paths, right? So in this experiment, we're actually not returning paths, but only pairs of endpoints of paths. In a sense, this is a little bit unfair to us, because we always compute a multiset representation for all the paths. And these systems here, they don't do that. They just compute pairs of endnodes. We compute the multiset representation, and then we use this to compute all the pairs of endnodes. But then if you look at the results, you see that the path multiset representation performs better. Yeah, so you have a lot fewer timeouts. Average time is the fastest one, even up to around 10 times faster than the competition, and same for median runtime of these queries, right? And we even compute something that allows you to do later computations on all the paths that are the result of the query. Okay, so to conclude, path multiset representations are a new concept to succinctly represent paths in graphs. They have a solid theoretical basis, and they can speed up things drastically. We are only beginning to study them, and we want to think about a whole bunch of future questions next. Thank you.